Hi everyone. In today's video, we will be covering Chapter 8. Please note that Chapter 8 is actually going to be separated into two different videos. Reason being is this first video is going to focus on the overall conceptual framework of what hypothesis testing actually is, and at the tail end of it, we will get into one sample test. The second half of this chapter is going to focus on two sample hypothesis testing, and so that's what we'll complete in the second video. So recall that there are two ways that we can use sample data to estimate population parameters. So this is when we make inferences about our population. Chapter 7, and in the last video we covered, we focused on the idea of confidence intervals, which tells us that the population parameter, whether it is a mean or a proportion, lies within a certain range of values. Chapter 8 focuses on this idea of hypothesis testing, which is where we use inferential statistical tests that use sample data to evaluate the probability of a hypothesis about a population. And so that's what we'll be focusing on in today's video and the next one. So just keep that in mind as we move throughout each of these. So before we dive into the actual calculations of hypothesis testing, I want to make sure that we have a firm understanding of the overall logic of hypothesis testing. In other words, why are we doing this in the first place? What hypothesis testing allows us to do is estimate population parameters using sample data. It's just another way to do that, similar to confidence intervals. So whenever we do a hypothesis test, essentially what that allows us to do is test a research question. So if we have a particular interest in mind, we can use hypothesis testing to see whether or not our hypothesis or the idea that we might have about a particular phenomenon is supported or not. So let's dive into this graphic here. What we're seeing here is the idea between our hypotheses. So whenever we conduct a hypothesis test, we're always going to have two types of hypotheses that we're going to start off with. The first is called a null hypothesis, which is essentially our statement of no difference. In a criminological sense, this is very similar to the idea of a burden of proof. In a criminal case, that is beyond a reasonable doubt, right? Or the idea that people are innocent until proven guilty. So we assume people are innocent unless proven otherwise. And so that's where our statement of no difference comes in, right? We're not saying they're guilty or that they did anything. We're assuming the entire way that they are innocent just as they were before they entered the criminal justice system, unless proven otherwise. On the flip side here, on the right side of our graphic, our question essentially revolves around this idea of if there is enough evidence to prove guilt. So if we get enough evidence, in other words, if our statistics support our alternative hypothesis, we could find that the person is guilty. So in other words, we could find that there is a difference, right? That person actually did commit an offense that reaches that burden and they are found guilty. We call this rejecting the null hypothesis and accepting the research hypothesis, which is also referred to as our alternative hypothesis as well. You'll see those two different terms interchangeably throughout both this video and the next one, so just keep that in mind. Another way that we can approach this idea of the logic behind hypothesis testing is in terms of probability. So remember that under a normal curve, our entire area has to consist with either a proportion value of 1 or a percentage of 100%. So we're going to be revisiting this idea of the normal curve. In this case, if there really is no difference between the group and a larger population, again, re-invoking that idea of samples versus population parameters, then what's the probability that I drew a sample with this sample mean or proportion? Again, we're going to be using both in this case. Recall that within the normal distribution, the mean, median, and mode are clustered at that middle point, our 50 percentile. And because of that, if our sample mirrors what's in the broader population, then it's no different from one another, right? So that's our null hypothesis that we're testing here. You'll see me use this statistical notation throughout both this video and the next one, so know that we designate our null hypothesis with an H and its subscript of 0. So that's what you're seeing both here and on the right-hand graphic here as well. If the probability is unlikely enough, then we conclude that there is a difference between our sample and the population. So that would support our alternative or research hypothesis. The statistical notation for both our alternative and research hypothesis can be twofold. You can either use H1 or HA, whichever you prefer. You're going to see them interchangeable throughout this video and in your book as well. So know that either is acceptable, but that they do mean the same thing. So again, overall in hypothesis testing, we'll have two hypotheses at play: our null hypothesis, or our statement of no difference, and the alternative or research hypothesis, which is essentially saying there is a difference between our sample and population parameter. Another way that we can discuss the logic of hypothesis testing is through revisiting this image of our normal distribution. In this case, recall that our normal distribution has clustered around our center point of a data distribution. In this case, it would be a test statistic of 3. We would find our mean, median, and mode values right here in the middle. 50% of our distribution is going to be less than this, and 50% is going to be greater than this value. But let's recall our discussion from chapter 6 and 7 about the idea of z-scores and how that allows us to test samples against population parameters. The more standard deviations that you deviate from the mean, the less likely that probability is going to be. And so what we're looking at here in terms of our null hypothesis, again, our statement of no difference, is what we would expect to see. If our sample mean, median, and mode is similar to our population's mean, median, and mode, then that's right on track with what we would expect, right? It's not very different than what our expectation actually is. And so our null hypotheses would be within this area here, roughly. It's going to depend on the problem and the distribution that we have. But again, just visually thinking through this idea of the normal distribution, our safety zone is going to be those areas clustered around our mean, median, and mode values of a normal distribution. So that's where our null hypothesis would remain true. Again, a value here would not be very odd, right? It would be perfectly compatible with our null hypothesis. If a population's mean is 4 and we get a value in our sample of 4.2, that's right on track. There's not statistically enough evidence for us to suggest that our sample is different than what we would expect in the population. However, if we find via z-scores that our null hypothesis does not hold, and we find evidence to support the research or alternative hypotheses, that would be when z-scores are in this area or are danger zones of our normal distribution. Remember that z-scores essentially tell us how many standard deviations we are away from our mean, whether that's in a negative or a positive direction. And so if we are many standard deviations away from what we would expect in our population parameter, that's something for us to consider, and we might find support for our research and alternative hypotheses. Again, the higher value of a z-score in either direction is going to pull you away from the normal probabilities that we would expect under our normal curves. And so that's essentially what we're testing, right? We can do that with many different scenarios, and we'll get to some of those examples later on in this video, but just keep in mind this overall logic of what hypothesis testing is doing. There's very specific language that we use when conducting hypothesis tests, and because of that, I want to make sure we're all on the same page about what our claims, languages, and symbols will be before we actually conduct a hypothesis test or run any of our statistical analyses. So let's first start off with the null hypothesis. You'll hear me refer to this a lot as the statement of no difference. In other words, there is no effect in the population. So essentially, our sample is matching up to what we would expect to happen in the population. We designate our null hypothesis using H0. So if I ask you what the null hypothesis is in a particular research question later on in this video, you will actually be using this symbol here rather than writing out the term null hypothesis. So keep that in mind. Alternatively, our research or alternative hypothesis is the exact opposite of what we would expect in the null hypothesis, or in other words, that there is an effect in the population. We designate this through HA or H1. Either one of those is completely acceptable. You'll see me use them interchangeably throughout this lecture, and you might see them even interchangeable throughout your book. So keep in mind that they are referring to the same thing. In terms of the language of both the null and alternative hypotheses, they match up to what our claims are. So for our null hypothesis, there is no effect or no difference or no relationship or no change. With our alternative hypothesis, it's the exact opposite again. There is an effect, there is a difference, or there is a relationship between two variables, or there is a change. And we designate that using certain symbols. And so our equality symbols, again, meaning that there's no difference or there's equal, we oftentimes just use our equal sign, whereas when we designate inequality, it's going to be a not equal to sign. There will be some examples, though, where we're not just looking to see if there's a difference or not, but if there's a difference in a certain direction. So is it less than or greater than? And so that'll depend on the context of the problem, and we'll discuss that when we go through some examples. But just keep in mind that these are the options for the symbols when we write out our null and alternative hypotheses. As I had alluded to at the beginning of this video, there are different ways that we can go about conducting hypothesis tests. The first is a one-sample hypothesis test. That's where a mean or a proportion of a group is different from the larger population. So another way we can think about that here is it's group one versus the entire population. Two-sample hypothesis testing is a little bit different than one sample, and that's why I've separated these into two different lectures. The biggest difference between the two is that two-sample hypothesis testing, just in the lead-in of the name here itself suggests, is that it's two different groups or two different samples that we are testing against one another. So you can think of this as group one versus group two. But for the purposes of the rest of this video, we will be focusing exclusively on one sample hypothesis testing. So just to reiterate, one sample hypothesis testing is if a mean or proportion of a group is different from a larger population. And so within a criminological context, we could think of this in terms of a research question of, are senior citizens more likely to be victimized than the population in general? So our group, or group one in this case, is senior citizens, right? We are only concerned with this particular group and sample of population. We are comparing that, though, to everybody else, or the entire population. And so that's what we have here on the right. And so we could fill this in with any certain group that we might be interested in. It could be juveniles, or males, or females, or people of a certain race. It's gonna depend on what our research question is actually asking us, but what will not change is this second group here, against the population. So that's your key when determining if it's gonna be one sample or two sample. Do I have one group of interests that I'm comparing to an entire population, or am I comparing two different groups to each other? So keep that in mind as well. Just as a revisiting here before we dive into our steps of hypothesis testing, are distinguishing between our sample statistics and population parameters. You've seen this chart in previous videos, so I won't spend too much time on it here, but if you do need a refresher, the main ones that we will be working with here are means, proportions, and standard deviations, also a little bit with sample sizes here at the bottom. And so just keep in mind that we do have different statistical notation depending on if we're working with means, proportions, and standard deviations with reference to whether it's a sample statistic or a population parameter. That's going to be especially important with one sample hypothesis testing because our samples are going to be designated by this first column, whereas the population parameter will be designated by this second column. So let's dive into our steps of hypothesis testing. You will also hear me refer to this as the 5-step model. So on a future problem set or a quiz, if I ask you to conduct the 5-step model of hypothesis testing, that's what I'm referring to, this slide here. As another note, these are 5 general steps, meaning that they can be applicable to both one sample and 2 sample hypothesis testing. You'll actually see this exact slide on the very next lecture video because we can use it in either scenario. So with those 2 things in mind, let's start off with our very first step. This is where we make assumptions. What we're essentially doing at this step is ensuring that we can actually answer our research question using hypothesis testing. There's a couple things that we kind of have to check off in order to make sure that we can actually test this. This will become a little bit more clear on the very next slide, so I'm not going to spend too much time on it here, but just know that step 1 is to make our assumptions. Step 2 is where we deal with our hypotheses, so both our null and our research or alternative hypothesis. There's a second component here in terms of selecting the alpha level, but let's first start off with our hypothesis discussion. This is where we're going to state the null hypothesis. And the way we do this is through statistical notation rather than actually writing out the word null hypothesis. We're going to do that through our designation here of H with a subscript of 0 for the null hypothesis. For the research or alternative hypothesis, you can either use H with a 1 or H with a subscript of A. Either one of those are acceptable. You'll see me use either of those throughout the duration of this lecture, and you might see them both used in your book as well. So know that those are both referring to the research hypothesis and that you can use either one. The second component here is to select our alpha level. What we're doing here is taking a look at the context of the problem because I will always tell you what alpha level I want you to use. However, what your job is here is to find the corresponding statistical information that's going to be necessary for our test statistic using that alpha level. And I think that one will make a little bit more sense in the context of an example as well. So hang on to that for right now. Step 3 is to select our sampling distribution. This is the type of distribution and specifying our test statistic. Essentially, what I want you to do in step 3 is take a look at the problem and determine if we're using proportions or means. That's going to have an influence on step 4 when we get to computing our test statistic. So it's really important for us to figure out which one we're using because there's 2 different formulas depending if we're using means or proportions that we'll have to use at step 4. Once we compute our actual test statistic, that's where we can get to step 5, which is making a decision and interpreting the results within the context of the problem. As I had mentioned on a previous slide, hypothesis testing uses very specific language, and step 5 is no exception to that. At step 5, we can decide to either reject the null hypothesis or fail to reject the null hypothesis. We won't be accepting anything or saying one is true versus the other. Reason being is back to an idea we mentioned way early in the semester about not being super confident or 100% confident at any given time. So we can't say our null hypothesis is true or our alternative hypothesis is true, right? We can have a certain level of confidence, but in statistics, it's very rare for us to just blatantly say, yes, this is a fact, this is true. Because of that, let's talk about the interpretations of both rejecting or failing to rejecting the null hypothesis. If we reject the null hypothesis, this means that the evidence from our sample is strong enough to conclude that the null hypothesis is unlikely to be true. In other words, we have found a statistically significant effect or difference. If we fail to reject the null hypothesis, this means that the evidence from our sample is not strong enough to conclude that the null hypothesis is false. So, another way to think about this is that we do not have enough evidence to say there is a statistically significant effect. But again, that doesn't mean that the null hypothesis is true. So that's why we're using the specific language here of either rejecting or failing to reject rather than accepting either or. And so these are the 2 options when I say interpreting the results within the context of the problem. We're going to start off our conversation with either we reject the null hypothesis or we fail to reject the null hypothesis. The next couple of slides are going to cover each step of the 5-step model in a little bit more detail, but it's going to be a general overview, so it's not going to be specific to a single problem. We'll do 2 examples at the conclusion of this lecture, covering both a 1-sample hypothesis test for means and a 1-sample hypothesis test for proportions. So keep that in mind. Again, these are just going to be the general steps. So with that in mind, for a 1-sample test, the first thing we need to do is make our assumptions. These are going to be specific to a 1-sample test, so this is going to look different when we discuss 2-sample hypothesis testing in the next lecture video. But for right now, there are 3 key assumptions that we need to make in order to proceed to the subsequent steps of our 5-step model. The first is that we are working with a random sample. And so if we do not meet this requirement, or we see any language within the context of our problem or an example that suggests that we are not using a random sample, we cannot conduct a hypothesis test. And so this is our first checkpoint here. We need to ensure that we're using random samples. The second goes back to our ideas all the way from chapter 1 about levels of measurement. In this case, the variable we are testing needs to be interval ratio if we are using sample means. And so this is another checkpoint for us. Although, if we are using sample proportions, our variable has to be measured at the nominal level. And so again, this is going to depend on the context of the problem where we determine are we using means, averages, or proportions. And once we do that, we need to ensure that for means, it's an interval ratio level variable. And for sample proportions, we need to ensure that it is measured at the nominal level. So we need to check off that one as well. Lastly, it has to revolve around this idea of sample sizes. So going back to our discussion about the normal curve in general, we saw that the more our sample size increased, the more normal our curve became. That's the same idea we're dealing with here. So we need to ensure that we are dealing with a sample size of at least 50, because this is going to suggest that our distribution will be normal. And so that deals with step 1 here as well, both the randomness and the normality of our curve. And so we need to ensure that both of these are set before proceeding with any of the other steps. Again, these are specific to 1-sample tests, but all 3 of these components must be met in order to go to step 2. The second step revolves around the idea of hypotheses. We have to establish 2 here, both the null and our alternative or research hypothesis, but let's first start off by discussing our null hypothesis. As a reminder, our null hypothesis has to be designated in statistical notation. So here it's going to be H with the subscript of 0. This is our statement that there is no effect or no difference, and it serves as the default or the starting assumption that the parameter of interest in the population is equal to a specific value. In a 1-sample test, the null hypothesis is the statement of no difference, and as a last reminder, the difference between a 1-sample and a 2-sample test is that a 1-sample test is comparing one group to the greater population, whereas the 2-sample test, we're going to be comparing 2 groups to one another. Let's take a look at an example in which we can actually formulate the null hypothesis within the context of a research question. Here, our research question states, is the average number of overtime hours worked per week by police officers in St. Louis County different from the national average of 10 hours? Something that I noticed right away about this research question is that I can confirm that I am conducting a 1-sample hypothesis test. Reason being is that we only have one group, St. Louis County police officers, in comparison to a broader population, or the national average. The second thing that I can note is whether or not I'm using proportions or means, and this is going to be important for the statistical notation of our null hypothesis. Here in this example, I see the word average, which should trigger for you that we're dealing with means. So written out, our null hypothesis states that the average number of overtime hours worked by St. Louis County police officers is equal to the national average of 10 hours. But remember that when we actually write out our null hypothesis, we will be doing this in statistical notation. That's what I have written out here below. I start off with my symbol that represents my null hypothesis, or H0. And because our null hypothesis represents our statement of no difference, that's why I have my equal sign here. We're not expecting our St. Louis County police officers to be different than 10 hours. That's why I have that equal to that here, because that's what we're testing against. And the last thing that I just alluded to was our statistical notation for means or proportions. If you take a look back at the chart earlier in this slide, it's going to designate the certain types of denotations that we're going to use, whether or not we are using proportions or means. And for means, we use mu. If this question asked you about the proportion of officers that work overtime compared to the national average, we would have seen the symbol here of pi instead. And so that's why it's important for us to note right away when we're first looking at our research question, whether or not we're dealing with proportions or averages and means. That's also going to help us in step 3 later on, but especially here for the context of our hypotheses with both the null and research and alternative hypotheses, we need to make sure that we're using the proper statistical designations here. Again, because we're using averages and means, we use mu. Once we establish our null hypothesis, we also have to determine our research or alternative hypothesis. We can designate this 2 ways, either through HA or H1. And again, this is our statement that the group is different from the population mean or proportion within the context of a one-sample test. The research hypothesis is what the researcher aims to support through the data collected. The reason that I have both of these symbols written here is that it's going to depend on whether or not we're using sample means or sample proportions. So again, with proportions, we're going to have our pi symbol here, and with means, we're going to have mu. And there's a couple different ways that we can go about determining our alternative or research hypothesis. And this comes directly from the context of the problem. So is it a statement of difference? Link back to the example we just had on the previous slide. We'll get to that in a second here as well. But about the number of hours worked for overtime. We could say, is the St. Louis County Police Department different than the national average? Are they greater than the general population? So are they working more than 10 hours per week? Or is that group of St. Louis County police officers working less hours of overtime compared to the general population? In the context of this example, we just had a statement of difference. Are we different from the national average or not? So we would use the not equal to sign here. It's opposed to our null hypothesis, which had an equal sign. But as I mentioned, if the research question stated whether or not St. Louis County police officers worked more than the general population of overtime hours or less than, our symbol could change to accommodate that research question. So that's another important aspect as we're working through this step 2 of establishing our hypotheses, especially with the research hypothesis, of what symbols we're using on the front end. So again, proportions versus means, and also, is it different from the population? Is it greater than the population? Or is it less than the population? And that's going to depend, again, on the research question. Let's revisit our example regarding the average number of overtime hours worked among St. Louis County police officers in comparison to the national average or that broader population. Remember that with our null hypothesis, that is our statement of no difference. In other words, we don't have a reason to suspect that the St. Louis County officers are working any different than the national average in terms of overtime hours. Our alternative hypothesis, though, suggests otherwise, right? It's the alternative to our null hypothesis. And as I had mentioned on the previous slide, there are 3 ways that we can go about establishing our research hypothesis. And that depends on the context of the problem. Are we wondering whether the officers are working a different amount? That would be designated by the not equal to sign. Are we concerned with whether they're working less than the national average? That would be designated by the less than sign. Or are we concerned with whether or not they're working a greater number of overtime hours in comparison to the overall population? and that would be designated with a greater than sign. To figure out which of the three options we're going to be using, we have to look at what our problem is specifically stating. Here, I see the word different, which shows to me that I don't care in what direction my distribution is going to settle on. It could be that St. Louis police officers are working more than the national average or less. Different implies that it could be either end of our distribution. We're not picking a side here. We just want to know if it's different than 10. So a way that we could write out our research hypothesis is this. The average number of overtime hours worked by St. Louis County police officers is not equal to the national average of 10 hours. But again, we have to show this within the context of statistical notation. So the way we go about that is this below. I have stated here H1 to designate my research hypothesis, but also remember that you could have HA here as well, and that's perfectly fine. Similar to how I had in my null hypothesis, we're still dealing with means here, which is why I have the mu symbol. Of the three options that I mentioned on the previous slide regarding whether it's going to be a difference than, less than, or greater than, my key word here again is difference. So that's why I have my not equal to. The 10 comes from just the number of hours that our research question is suggesting. Again, the national average is 10 hours. So our null hypothesis is that mu is equal to 10, and our alternative or research hypothesis is that mu does not equal 10. The second component to step 2 is selecting our alpha cutoff. This information will always be given to you within the context of a problem or an example, but I want to make sure that you understand what alpha functions as within the broader context of hypothesis testing. So as a brief reminder, alpha is the probability or cutoff at which the null hypothesis is rejected. Essentially, alpha is serving as our barrier between the danger zones on either end of our distribution. We usually want pretty strong evidence to reject our null hypothesis, so we usually choose a pretty small alpha value as our cutoff point. Do we want to be 90% confident? We would choose an alpha cutoff of 0.1. If we want to be 95% confident, we would choose an alpha cutoff of 0.05. And lastly, if we want to be 99% confident that our null hypothesis doesn't fall within either of those rejection zones, we would select an alpha value of 0.01. So again, alpha is the probability of rejecting a null hypothesis that is true. These are those common values, and these are the only ones that I will mention in the context of any other problem or a quiz. So these are the only three that you need to know. Moving on to step 3, selecting our sampling distribution and specifying our test statistic. Again, this is specific just to one sample testing. For a one sample test, the sampling distribution is the probability distribution of all possible sample means or proportions. In this case, again, our alpha values here, which is what you see as this little symbol here, serves as the barriers of our rejection zone. So if our test statistic falls into either shaded region here, we will reject our null hypothesis. Here in the middle, if we fail to reject our null hypothesis, that means that our test statistic fell within our safety zone, or right here in the middle. And so if it helps you to visualize it this way, I encourage you to write out a little template like this of a standard normal curve, and it'll be able to tell you in reference to our alpha cutoff points whether or not our test statistic fell into that safety zone or our danger zones on either end. Another component of step 3 is to determine whether or not we are conducting a one-tailed or a two-tailed test. What does this mean? This is a new term for us, so let's take a moment to discuss this. Essentially, what a tail implies is what end of the distribution do we care about? Which tail? Are we concerned with the positive end, the negative end, or both? The way that we can figure that out is through the research question and specifically our alternative hypothesis. Remember a few slides ago, we saw that there are 3 different ways that we can determine our research hypothesis. Whether or not we're interested in whether our sample is different from the population, whether it's greater than the population or whether our sample is less than the population. And that key term there is going to determine what type of tail we're dealing with. So let's take a look at this graphic on the left. If our research question and our alternative hypothesis specifies that we're interested in whether or not our sample is greater than the population, then we are only interested in the positive end of the distribution, or just one tail. That's where we get that term from there. Alternatively, if we saw that our research question and our alternative hypothesis asked us whether or not our sample is less than the population, then we are only concerned with the negative end of the distribution, so only one tail. It depends on what end of the distribution we're concerned with and how that's specified, so that's why it's really important to look at the language of both the research question and in step 2, our research or alternative hypothesis. As I alluded to on the previous slide, there are 3 options though that we can use in terms of determining whether or not it's one-tailed or two-tailed. Our example for a two-tailed test has to come down to this idea of whether or not our sample is different from the population. If you see the word different, what this implies is that we don't care about the direction of the distribution. It could be less than or greater than. We don't care. Because of that, we have to designate both ends of the distribution. So that's why it's a two-tailed test, because we are considering both tails, negative and positive. You also see here that we use the not equal to sign. This is important from step 2 because what this implies is that we don't care about the direction of our sample either. Maybe we don't know how many police officer hours of overtime are worked in that respective precinct. And we have no idea how that's going to relate to the national average. We could think we are well above that or well below that. We don't know. And because of that, we could specify both directions here by just stating whether or not we think our sample is different from that national average of hours. What you're taking a look at here is an image in which it depicts a one-tailed test using an alpha cutoff point of 0.05. So remember that in a one-tailed test, we're only concerned with either end of the distribution, whether that's positive or negative. Here, I have an example of what it would look like with an alpha cutoff point of 0.05 in a positive distribution. So if we were interested in whether or not our sample was greater than the population. What I want you to pay attention to here is that in a one-tailed test, our alpha cutoff point is going to be the entire alpha region, or the entirety of the 0.05%. Whereas in a two-tailed example, we have to split our alpha cutoff point in half to account for both ends of the distribution. So in this case, you can see that our same alpha value of 0.05 has to be evenly split into 0.025 here on the negative end and 0.025 on the positive end. Another critical reason we have to determine whether we are using a one-tailed or a two-tailed test is because it's going to determine our associated z-critical scores, those boundaries within our standard normal distribution. And so what you're looking at here are common critical regions for alpha cutoff scores. I will never ask you about any other alpha scores beyond these 5, so take particular note of this as you move forward on problem sets and future quizzes. Why it's important for us to determine whether or not we're using a one-tailed or two-tailed test is because our z-scores are going to be slightly different in our critical regions depending if it's on a one-tailed or two-tailed test. As you saw in the previous 2 slides, if we had a difference situation where we care about both ends of the distribution, our alpha cutoff score got sliced in half to account for that 0.05 value having to be 0.025 on one end and 0.025 on the other end. So you'll see that the two-tailed values here are slightly different than a one-tailed value. I'm not going to spend too much time on this slide simply because this isn't something you have to memorize. Use it as a reference moving forward. But again, these are serving as those boundaries of our cutoffs of our danger zones. So let's say we have a two-tailed value, and that's why you see the positive and negative direction here, because it's accounting for both ends of that distribution. If we have a z obtained, meaning that our test statistic exceeded a value of positive 1.65, if we were using an alpha value of 0.1, then we would know that fell into the danger zone. Therefore, we would reject our null hypothesis. So this is where we're boundary setting here. This is the last component of step 3, and we will move into step 4 here in a second about computing our test statistic. Our test statistic is going to depend on whether or not we are using sample means or sample proportions. You heard me use the language on the last slide about z obtained. So what we're ultimately going to do in step 5 is compare the value of our z obtained, which is basically our test statistic. What did we calculate in comparison to those alpha cutoff points in those z critical regions that we just discussed on the last slide? But again, step 4, the only thing you really need to take a look at here is whether or not we're dealing with means or proportions. You can see that the formulas here are different from one another. And so if we select it incorrectly, we are not going to get the correct test statistic or our z obtained value. So ultimately, our entire calculations are going to be off. Okay, we have finally made it to step 5. This is where we get to actually make a decision about what our z obtained or our test statistic, which is what we calculated in step 4, means in relation to our z critical value, or what we established in step 3. What are our boundaries of our critical danger zones there on the end? And when we compare those two numbers to one another, that's when we can make our decision. Remember that hypothesis testing uses very specific language, and because of that, we have two options here at the last stage. We can either reject the null hypothesis or fail to reject the null hypothesis. Our first option is to reject the null hypothesis. So if our z obtained, meaning our test statistic, whatever we calculated in step 4, is beyond our z critical value, meaning that if we had a normal distribution and we had z critical values here on either end, and our z obtained fell in this region here, it exceeded or fell beyond our z critical value, we reject the null hypothesis. So take a look at whatever your z critical is here and whatever that value is. And if your z obtained or your test statistic is greater than this on the positive end of the distribution, or if this was a statement of difference, if it's less than our distribution here on the other end, then we would reject the null hypothesis. However, if our z obtained is not beyond our z critical, we fail to reject the null hypothesis. So written out here on my standard normal curve, we set our two z critical boundaries here. Let's say our z obtained falls within our safety zone here. We would then fail to reject. And so a way I like to think about this is I sometimes map this out myself when I'm working through these problems. My fail to reject zone or my safety zone is going to be the middle of my distribution. Let's think back all the way to the beginning of this lecture, where we know in a normal distribution, our mean, median, and mode are always going to be our center point. And so if our z obtained fell right here, we have no reason to believe that our sample is significantly different from the population. And so we're safe there. There's no reason for us to suspect that it's different. However, if our sample value falls into our danger zone over here, this is our rejection zone. So let's say within the context of the previous example we've kind of been mentioning throughout this section about the number of police overtime hours worked at St. Louis County, we know that the mean or national average was 10 hours. So let's say we find out that St. Louis County police officers are working 11 hours. That's not enough for us to suggest that it's significantly different than the national average. But let's say we find out that they're somewhere all the way over here. They're working upwards of 22 plus hours per week. And if our z obtained did show this, that it fell within this critical region, this would be a difference enough for us to suggest that it's different from the national average. I'm just making up these figures for the sake of conversation, But again, you can think of this as your fail to reject zone here in the middle, or your safety zone, in your danger or rejection zone out here. So once you establish your Z critical values in step 3, map this out if it's helpful for you. Establish what end you're dealing with. If it's a statement of difference, then you're going to have Z critical values on both ends. But if it's a value, whether it's greater than or less than, remember it's a one-tailed test, so it's only going to be in one direction. But again, you can establish where your cutoff points are, and then it helps to visualize where your Z obtain actually fell. Are you safe here in the middle, or are you in the danger zone on an end, and then we would know to reject it. Okay, I know that was a lot of new information in terms of the logic of hypothesis testing and our 5-step model, but I'm hoping the next 2 examples help kind of bring all those pieces together as we work through some tangible examples. The first one we're going to go through is a 1-sample test for proportions. So even though I'm telling you this is for proportions right now for the sake of the example, on future problem sets and quizzes, I will not be specifying whether or not something is 1 sample or 2 sample or proportion or means. That is something that you are going to be responsible for determining from the context of the problem. So keep that in mind. Again, I'm just specifying it here so that we're all on the same page of what this example is showing us. Let's start off here. In a sample of 63 arson cases, 12 were cleared. Is the proportion of cleared cases in this sample significantly different from the population proportion of 0.23 at an alpha level of 0.1? So a couple of things here. Although I already mentioned that this is going to be an example of a proportion in a 1-sample scenario, the way that I would know this without having that information is by looking at the problem. And there's 2 key indicators here. The first is that I don't see any mention of the word average or mean, and I have tangible numbers here, 12 and 63. And I know that I can calculate a proportion by taking 12 divided by 63. And that will give me my proportion of cases that have been cleared within that sample. I am also comparing 1 sample to an overall population. So that's where I get 1 sample. I'm not comparing the rates from the state of Missouri to the state of Illinois. It's only my 1 sample versus an entire population. Here, we're using Uniform Crime Report, or the UCR data, which is a national reporting agency. And so that's where I get that national or population level data. So I'm comparing just my sample to that national proportion. Here on the chart on the left, you can see that I have them designated in percentages. Again, oftentimes in tables and figures, we do see percentages used because it's easier for us to interpret those rather than proportions. But note that we can also calculate proportions fairly easily from percentages simply by dividing our percentage value by 100. So that's what I have listed here. Our pi value here is designating our proportion of 0.23, or the national proportion of cleared cases is 0.23 or 23%. One other thing we're going to want to keep in mind as we move through our 5-step model is this alpha level of 0.1. That'll become important as we go throughout the steps of this 5-step model. But as I had mentioned on a previous slide, I will always tell you what alpha level to use. So a couple of things that we can pull out of our question before even getting started with our 5-step model. I'd mentioned a few of these on the previous slide, but our question specified that I had a sample of 12 arson cases that were cleared out of an entirety of 63. So I had mentioned that we could calculate our proportion value by doing 12 divided by 63, and that gives us a proportion value of 0.19. Because we're using a 1-sample test for proportions, we're also going to need our n value of our sample, so we're going to have n equals 63. We'll just keep these figures in mind as we go about calculating our test statistics. But again, this is a good first thing before we even jump into the 5-step model to make sure that we know from the context of the problem what statistical information we are going to need in order to answer this question. Okay, let's start off with our very first step of the 5-step model. And again, these are general steps, so we're always going to be starting with this one, regardless of if we are doing a 1 sample or 2 sample, or a test for means or proportions. In this case, there are specific assumptions, though, for a 1 sample test for proportions. And recall that for assumptions, essentially what we're doing here is just ensuring that the information provided in the problem allows us to conduct the proper hypothesis test. So again, this one is specific to 1 sample assumptions for proportions. So the very first one is that we are working with a random sample. You can assume that any problem I am going to give you within the context of this class is going to be a random sample. And so we can check that one off right away. If you were to see this in a real life example, you would just want to make sure that there's some language in there about a probability sample or that it was randomly selected in order to check this one off. But again, for the purposes of this class, I'm never going to give you a non-random sample. The second one, and this is one that is specific to proportions, is that the variable we are testing is nominal. So that's a way for us to go back and check and ensure that the variable of interest is measured at the nominal level, and that is necessary for us to conduct a hypothesis test for proportions. So looking back, we know that arsons, and cleared arsons in this case, is a nominal level variable, right? It's a type of crime. The way that we measure it doesn't inherently have any order to it, and it's essentially a yes-no variable, right? If the arson was cleared or not. So we can check that one off. And lastly, knowing that we have a sample distribution of above 50, this will ensure that it will be normal. If you look back at the example that we are going over here, it is over 50. So we satisfy this assumption as well. So we'll move on to our next step. Step 2 is where we state the null and the research hypotheses. So a couple things to note here, and this is going to also depend on the context of the problem. 1, remember that our statistical notation is what we will be focusing on here. So for the null hypothesis, we will always designate it with an H and a subscript of 0. For our alternative or research hypothesis, you can either designate it with an H with a subscript of 1 or an H with a subscript of A for alternative. The second piece I want you to pay attention to is the symbol that we use statistically to designate either a proportion or a mean. And since we are dealing with proportions specifically, we are going to use the pi symbol. We'll get to means in just a bit, and that's where we use our mu symbol. But again, for proportions, we need to ensure that we are referring to the proportion value of pi here. Secondly, we need to ensure that our null and research hypotheses are matching up with the context of the problem. And so in this case, we have the proportion of cleared arsons is no different than the population, and that was a value of 0.23. I got that directly from the problem itself. That's essentially what we're testing against. And remember that our null hypothesis is our statement of no difference. That's why you see this equal sign here. The last component that you will want to be mindful of when constructing your null and research hypotheses is the symbol that you use for your research hypothesis. You could have a couple different options here depending on the language used in the problem itself. Here, we're just merely interested in whether or not our proportion of cleared arsons is different than the population. And because of that, if we think of this in terms of our normal distribution, put my little mean there in the middle, different simply implies that we could be interested in whether it's greater than or less than. And because of that, it's a two-tailed test. I have it on both ends of my distribution. And so we use the not equal sign to designate terms that are different from each other, but know that this could change depending on if we were interested in whether our proportions of cleared arsons was less than the population, we would use a less to symbol. Or if we were interested in whether our proportion of cleared arsons is greater than the population, we would use a greater than symbol right here. And so just keep that in mind. Again, we are using the not equal to sign because our problem specifically said different, but know that that could change depending on what type of problem we have. Step 3 is to select our sampling distribution and specify our test statistic. And so we know that for a 1 sample hypothesis test for proportions, we will be conducting a z-test, and we've already ensured via our assumptions that we are working with a nominal level variable, so all of this is satisfied. The next component is making sure that we know the associated alpha value and z-score, because we'll need this for our calculations later on. So again, using our little cheat sheet here, I know from the question that we will be working with a 0.1 alpha level. Because of that, our two-tailed value, and we kind of talked about that on the last slide because we know from the language of the problem that we're interested in whether our proportion of cleared arsons is different from the population. We care about both ends here. And so that's why we are doing a two-tailed test. If it would have asked us again about a greater than or less than situation, that's when we would be focusing on this right-hand section here with a one-tailed value. But again, alpha level directly from the problem indicates to us that we will be using it as the 0.1 level, and the associated z-value is plus or minus 1.65. So just as another way to visualize what we've done so far between step 1 and the end of step 3 here, I wanted to show us what this question looks like relative to our normal curve and distribution. So remember that our safety zone here in the middle is our fail to reject zone. So if our obtained test statistic falls within this white region here, we will fail to reject the null hypothesis. Our danger zones, which are set up by our critical values here on the end, if our obtained value or test statistic falls within these shaded regions here, we will reject the null hypothesis. One other thing that I want to point out here as well is just a brief reminder that when we have an alpha level, in this case of 0.1, but we have a two-tailed test, those associated values will actually be divided by 2 because we have to account for both ends of the distribution. So in terms of area, each danger zone is essentially a proportion value of 0.05 or 5%. Step 4 is where we actually compute our test statistic for our one sample test. And as we had mentioned earlier in this presentation, there are 2 different formulas depending on if we're using proportions or means. So in this case, I am adopting our one sample proportions formula here. Based on the problem, we know a fair amount of the information that we're going to need to plug in here. We know that our sample proportion value is 0.19, where the population proportion is 0.23, and my sample contained 63 observations. And so this is what it would look like if I plug in those numbers. So I'm just showing you the math step by step here. And so starting off, if I were to just plug these in, I would put our sample proportion right here at the top of 0.19 and subtract that by our population proportion of 0.23. I then divide that by the square root of our population proportion multiplied by 1 minus our population proportion divided by our n, or 63. Again, each of these steps here are me just going through the math so you can double check yourself along the way. And the ultimate result we get for our z obtained is a value of negative 0.755. Okay, we have reached our final destination for this example, step 5. This is where we make a decision regarding our null and research hypotheses and interpret our results. So this is our opportunity to compare our z critical value, which is what we establish in step 3, to our z obtained value, or our test statistic, which is what we just calculated in step 4. And so what conclusion do we make here? Well, we know that our z critical value is plus or minus 1.65. Again, this is the associated alpha value for 0.1 of a two-tailed test. And again, that came from our language of the problem being different. So we have both ends here, and our z critical cutoffs on each respective boundary are that negative 1.65 and the positive 1.65. We know that our z obtained value is only negative 0.755. And because of this, we actually land within our safety zone, or the fail to reject zone of our null hypothesis. But what does this actually mean within the context of the problem? Right here in the bold is a model that you could use to interpret questions like this and your ultimate results. And so I encourage you to adopt a framework similar to this when interpreting your problems. And so let's go over this one relative to this example. Given that our z obtained value of negative 0.755 does not fall into our z critical region, again, we're referring that it did not fall into this danger zone or shaded region over here or on this side, we reject H0, which again represents our null hypothesis, and conclude that the proportion of arsons cleared is not significantly different than the national proportion of arsons cleared. Essentially, we are reaffirming our null hypothesis that there is no difference between the proportion in our sample and the proportions nationally of arsons cleared. And so just keep that in mind. You always want to relate your results back to the initial problem. So now that we've completed an example for one sample hypothesis test for proportions, let's go ahead and do the same thing but using means. The monthly violent crime rate across cities throughout the United States is 60.56 per 100,000 population, with a standard deviation of 19.426. During COVID-19, a sample of 77 cities is found to have an average crime rate of 42.392 per 100,000 population. Our average crime rates during COVID-19 significantly lower than the average crime rates in general at an alpha level of 0.05. So as we know, there's a lot of information that we can pull from this initial example and problem that we will need later on to answer this question. And so we'll revisit this in just a little bit. Our first step, same as we did for our one sample hypothesis test for proportions, is to check our assumptions and make sure that we're meeting those in order to proceed with all of the subsequent steps. And so again, the first one is that we are working with a random sample. We can check that one off because again, there was no indicator that it wasn't a non-random sample. The second, and this is where we differ from our sample proportions, is that when we are using means, we have to ensure that the variable we are testing is interval ratio. And we know that with crime rates, it's something we can count, right? Each individual crime has its own value of one crime, 2 crime, 3 crimes. And that's something we could measure in between two. If one city had 60 crimes and the other city had 40 crimes, we'd know the first city had 20 more crimes than the second one. And so it's measurable and we have those fixed intervals in between. So we can check this one off as well. And we also know that we have a sample of greater than 50, so we've met all of our assumptions that we need to in order to proceed with our next step. Our second step is to state our null and research hypotheses. So a couple of things we want to be mindful of here. The first is that we are still referring to our null and research hypotheses in terms of statistical notation. So our null is always going to be represented by H0, and our research hypothesis is going to be represented by H1 or HA. So the next thing I want you to pay a little bit of an extra attention to here is that our symbol has switched. Where in the previous example, we were dealing with proportions, so we used the pi symbol. Here we're dealing with means, and so our symbol switches to mu instead of the pi symbol. The second thing is that our statement of no difference here with our null hypothesis will always be started with an equal sign. That's going to be the same regardless of any type of hypothesis test you are conducting. And lastly, we want to ensure that we are including the correct statistical information here, which is the crime rate within the population, because that's what we're testing against. Another thing that's a little bit different here compared to our example with proportions is the symbol that we are using for our research hypothesis. The language here is what we want to pay attention to within the context of the problem. So we wanted to know, are crime rates during COVID-19 significantly lower than crime rates in general? And because of that, we are using the less than symbol here because what we're testing against is whether or not our sample is less than that population average of 60.560. And so in terms of our normal distribution, the only end we care about is here. It's a one-tailed test, and we only care about the negative end of the distribution. As you saw in the previous example, when we had the term different, that implied that we didn't care about the direction that our research hypothesis could lead us in. It could be lower than that or greater than that. But here it is specifically using the term lower. And so we only care about that one end of the distribution, and that's why our symbol changes as well. So keep in mind those three elements as you construct your null and alternative hypotheses, regardless of what type of hypothesis test you are conducting. So as we move into step 3, which is selecting our sampling distribution and specifying the test statistic, we want to ensure that we are using the correct row here. So again, one sample hypothesis test for means, we have an interval ratio level variable here, and we will be using a z-test because our population standard deviation is known. Our third step is bringing together information from the initial problem in steps 1 and 2 in order to determine our z-critical cutoff points. And so with those things in mind, we know from the problem itself that our alpha level is 0.05. We also know that this is a one-tailed test because we specifically saw that the term lower was utilized in the problem. In other words, we were only interested in whether or not the crime rates during COVID-19 were lower than the population. And so we only care about the left end of this distribution here or the negative end. The corresponding z-critical cutoff point for an alpha level of 0.05 and a one-tailed test is negative 1.65. If we would have been interested in whether or not the crime rates were higher during this time period, then we would care about the right end or the positive end of the distribution over here. That would be our shaded region. And then our z-critical cutoff point would be positive rather than negative. But again, since we only care about whether or not it was lower, that's why we're specifically focusing on the left end or the negative end of the distribution here. Step 4 is where we compute our test statistic for sample means. You'll notice that our formula here has changed to accommodate us now using means rather than proportions. And so based on the problem itself, we know that our sample mean was 42.392 per 100,000 population. So we can go ahead and plug that in for y bar here at the top. The second component of information that we can get from the problem is our population mean. So that's going to be represented by mu. So we can go ahead and plug that in up here. It was a value of 60.560. It was also stated within the problem that the population standard deviation was 19.426. So we can go ahead and put that in for sigma. And lastly, our sample consisted of 77 cities, so that's going to represent N. What you see here is merely me plugging in the information that you saw on the last slide. So again, 42.392 represented Y bar, or our sample average. We subtract that by our population average, which was 60.56 crimes per 100,000 population, divided by our population standard deviation, which was 19.426, divided by the square root of N, which was our sample of 77 cities. You'll see in each subsequent step here that it's just me working through the math. So we ultimately get to a final answer of our Z obtained, or our test statistic, of negative 8.206. Now we've reached step 5, our final destination in terms of our example for one sample hypothesis testing for means. This is our opportunity to compare our z-critical value, which is what we established in step 3, to our z-obtained value, which is our test statistic, which we just calculated in step 4, to determine what conclusion we're going to make. As I previously mentioned, I find it really helpful to chart this out relative to our normal distribution, so that's what you see here in our left-hand corner. Notice that our fail to reject zone, or this entire white area, encompasses this entire right end of the distribution because it's a one-tailed test. So we only have one danger zone, one rejection zone. That's on the negative end because we're interested via the research question in whether or not the crime rates were lower during COVID-19. And so my Z critical cutoff point here is negative 1.65. I got that directly from the work we did in step 3. And our Z obtained came to a value of negative 8.206. So since that's more negative than our cutoff point, we did fall into our rejection zone, or this shaded region here on the left. Because of that, we can interpret this now using this bolded language again of our shell here, of how we would interpret this within the context of the problem. So we can say something along the lines of, given that our Z obtained value of negative 8.206 falls beyond our Z critical region of negative 1.65, again, we are more negative than our cutoff point, we reject H0, which is our null hypothesis, and conclude that the average crime rate during COVID-19 is significantly less than the average population crime rate in general. Okay, you have made it to our summary slide, which shows you the end of this presentation. But keep in mind that this is only part 1 of chapter 8. Part 2 in the next video is going to cover 2 sample hypothesis testing. But what we've covered in this lecture really started off our conversation about this idea of the logic of hypothesis testing, or why we even do this in the first place. And remember that hypothesis tests allow us to use sample data to estimate population parameters. Confidence intervals allow us to do this as well, but this is just another way we can go about answering research questions. Hypothesis testing specifically is an inferential statistical test that uses sample data to evaluate the probability of a hypothesis about a population. And again, this is where we're bringing in together all of the chapters worth of information that we've covered so far to use our statistical knowledge to actually apply it to answer research questions. In terms of how we actually go about that, we talked about the 5-step model. And remember that this is a general model, meaning that you can use it regardless of the type of hypothesis test you'll be conducting, whether that's 1 or 2 sample, or dealing with proportions or means. With that being said, though, we do know that there's a couple differences, especially when it comes here to our assumptions and stating our hypotheses, that are going to change depending if we're using means or proportions. So please keep that in mind as you're working through your problem set and ultimately on a quiz. If you have any questions about the first half of this chapter, please let me know. You can always attend my office hours or set up an appointment with me. And as always, I will see you in the next video.